the lambda calculus, I've just picked up to recap a little stuff about lambda calculus that we had discussed in the last class. So we have known that it has been developed by Church and Kleene, and it can represent all computable functions. That is, it is equivalent in its power to Turing machine. And it has proven to be a very good mathematical foundation for all functional programming languages, which are kind of variants of lambda calculus. And in fact, in the common programming languages that are procedural or object-oriented, they have also started imbibing programming style based on lambda calculus. The greatest example being C++, which now has lambdas starting from it, C++ 11 variant. So the basic concept of lambda is nothing but it is a function which is anonymous. So when we define in, say, our algebra, if we define a function q, which maps from integer to integer and multiplies the argument to create the cube of it, then the name cube is just a placeholder, as you can see. The actual operation, I'm on slide 13, the actual operation is what you do in terms of the computation. So we write it simply as lambda n, meaning that n is the parameter which is bound in this lambda notation, and n cube is the body of that function. And then you can apply it to an argument, which basically means that you replace n in n cube by the argument, what we, in terms of C, what we call the actual parameter, and you evaluate that function or apply that function. So these are the some of the parallels between mathematical notation of n mapping to n cube, lambda notation, and say C function, which I illustrated on slide 14. And now, if there are more than two parameters, naturally there is a question of which parameter is to be replaced, which formal parameter, or say the lambda variable, is to be replaced by what actual parameter. So in that, we noticed in slide 16 that we will put lambda for each one of the formal parameters, so to say, and they will be strictly applied on the left to right order. This left to right order is the key thing here. So when I write for n square plus m, if we do lambda n lambda m and apply it on 3, 4, then n is taken to be 3 and m is taken to be 4. Whereas if we have a different order, lambda m lambda n, then m is taken to be 3 and n is taken to be 4. So that is what that is the convention we followed in the lambda calculus. It is very similar to the convention that we follow in mathematics, which is also by positional order, or in C programming that we have already seen. So this is what this is the basic introduction we did. Now what we'll do is we will formally introduce the syntax of lambda calculus in the discussion today, and continue to look at a number of different examples of common lambda expressions, common functions that we can build out of them. So a lambda expression is very simple in its structure. And simplicity or that minimality has been the driving force for defining the lambda notation. And it shows that even with simple notation, we can achieve really, really complex results. So there are lambda expressions come in 4 varieties, or often it is also mentioned as 3 varieties. We'll see. What it means is every variable is a lambda expression. which is designated typically by lowercase letters. Then we have predefined constants. Constants that are assumed to be known a priori, based on which these lambda expressions are being defined. The assumption of what you take as constants and whether you assume constants is a question of the extent of purity of lambda expression that we are talking of. We will illustrate that more, but predefined constants could be values as well as they could be operations. Varieties which really build up lambda. One is called the function application. Function application in simple terms in kind of C programming is function evaluation. It is also called combination. And the other is lambda abstraction, which is basically defining a new lambda expression or a function definition, and parallels the function definition in C, C++ kind of languages. So if we look at the basic syntax of lambda calculus in the Backus-Naur format, then a lambda expression is defined either as a variable, lowercase identifiers, or as a constant, which is predefined, or as a combination where you have two expressions, one following the other, and just for simplicity of syntactic understanding, we have put a pair of parentheses around them so that the precedence immediately does not start playing a role of what a lambda expression means. So one expression followed by the other is a combination, and an abstraction is written as lambda, the symbol lambda, followed by the variable, which is kind of the formal parameter, followed by a period symbol, which is a part of the syntax. I'm sorry. Going back to slide 20 again. And then following that, there is another lambda expression. So basically, as you can see, that the first two rules define a lambda expression out of, variable and constant. And once you have lambda expressions, then you can use lambda expressions to define combinations or abstractions. So if I more in terms of the common shorthand, short form notation, then a lambda expression E is defined either as V, where V is a variable or a constant, or as a function application, that is E applies onto E. Of course, the actual E's will be different when we do that. Or a function abstraction where lambda V dot E is a function in terms of a lambda expression that we have created. So this is the basic syntax of lambda calculus. Now, as I said, the purity of lambda calculus means that it does not have a predefined constant. This is good, but it actually makes the development of the lambda expressions really very long. So what is commonly accepted is we will use pure lambda calculus, but we will allow predefined constants in that to make our life simpler. So what are the kind of predefined constants? For example, if we are working in the domain of, say, natural numbers, then we'll say the predefined constants are the numerals, which are basically the different natural numbers, 1, 2, 3, 4, 5, like, for example, 34. The other is the set of operations that you can do on this domain. So this notion of domain is not so concrete. We will, over the course of development of lambda calculus, we'll make this notion of domain explicit in the calculus. But for right now, let us just assume that we are working on the set of natural numbers where we have numerals, which are constants, and we have operations in the natural numbers, in terms of the natural numbers that are known to us. We know when we say add, we understand what it means. Or when we say mul, we understand what it means. Its definition is not to be provided in the lambda calculus. It's to be known as to what the multiplication of two numerals will mean. Similarly, we have successor function, we have square function, and so on. We will not try to list them, but we will assume them as and when they are required. And maybe if it is necessary, we will make a note that here, this is the predefined constant operation that we are making an assumption of. Okay. So just a simple example. This example is actually borrowed from Lisp. I mentioned about Lisp in the class last time, which is a list processing language. So it has some operations, constant operations. One is called head or char. Char was actually, it was a short form of content of the address part of the register number. Forget about that. That's more historical. It has no specific connotation in lambda calculus as such. It primarily is a head. So given a list, it returns you the first element of the list. And then you have tail or CDR, which is commonly pronounced as kudur. So kudur, the two, which gives you, the tail gives you the list after removing the first element. So the result of head is an element, result of tail is a list. Then you have cons or construction, which basically takes argument and returns a new list whose head is the argument itself. And you have a also another predefined function is empty, which takes a list and returns true if the list is empty, otherwise it returns false. And you have a predefined constant nil, which basically means an empty list, just a pair of parentheses. So lists are written as pair of parentheses. So some example, if you do const y nil, naturally nil means a null list, so it constructs a list out of given the null list. So y within parenthesis y becomes the basically the list that you have constructed. So it is very easy to understand that if I do a head on this list, I will get back y. And if I do a tail of this on this list, I will get back nil. Similarly, I can have is put inside a pair of parentheses, which means that it is a list itself. So I'll get a list comprising x and y. Again, the head is x and tail is the list containing y. So if I do, this is what is shown in the next two expressions. So this is how the lambda expressions are to be written, and which is just an example from what Lisp does. Let us introduce the notion of free and bound variables. In a lambda abstraction, the variable or the variables in general that is mentioned with the lambda notation are bound in the body of the abstraction. So v is the variable and e is the body of the expression. So if I do lambda v dot e, then this v variable v is bound e. All occurrences of the variable are bound, whereas all occurrences of all other possible variables are free. Right? So here's an example. Say lambda x, lambda y. They have an expression xy. I've put in parentheses, so it shows that this is an abstraction where x and y, they have lambdas on them. So they are bound in the first part of the expression. Then we have an application on that onto YW in the parenthesis here. So Y and W are free in the second part. So you can see that though syntactically we have two Y's. You have a Y in XY, you have a Y in YW. These two Y's are actually different. One is bound in the first part, whereas the second is free in the second part. And this might create some confusion when we try to do this kind of applications, but we will see how to handle that through certain renaming rules later on. So if I just put a parallel between this and say mathematical and function, programming language notations, then I have, say, 4 variables, n, l, s, and g. And mathematically, I say this is the mapping. Integer cross integer cross integer cross integer maps to integer. And this is the body that you basically add the 4 arguments. Suppose in lambda notation, we are writing it as lambda n dot lambda l dot lambda s, and then this expression. Then what will happen is n, l, and s, these are with the lambda. So in the expression n plus l plus s plus g, each of n, l, and s are bound. Whereas g does not have a lambda on it. So g is free. So look at that in the C function. In C function, this bound comes in with multiple flavors. For example, I'm just keeping the variable names same so that you can easily map them. So n is the formal parameter of this function. L is a local variable, and L is a local automatic variable, and S is a local static variable. So you can understand that the notion of these symbols n, l, and s are limited within the scope of this function body only. Any n, any l, or any s that occur elsewhere in the program has nothing to do with these symbols. So these are the bound variables. So in lambda, we are not distinguishing between what is lambda does not have a concept of or a local variable or static separately. So in lambda, all of them are basically lambda variables and they are bound. In C, they are bound in this way. Whereas outside of this function, before this function, I have defined a global variable g, which naturally this function has no role in putting the value of this variable g. It is to be set from the environment. So this is a free variable. So if I look at the corresponding function application, then F237G is 12 plus G. 2 plus 3, 5 plus 7, 12 plus G. When lambda notation, the same thing applied to 237 will give us give us 12 plus G, right? In a similar way. In terms of the C function, if I set G to 5, which is outside of the scope of this function, set it in the environment, then F2 will give me 17. Whereas if I set the global G as 3, F2 will give me 15. So it's basically, doing n plus l plus s. So given n is 2, this is 12, plus global is 5, so this is 17. Here global is 3, so 2n plus 3, 15. Right? So that is the parallel between our already under. So this was function abstraction. Now function application is, if I have an expression E1, E2, where E1 is a lambda expression and E2 is a lambda expression in parentheses, then and if E1 is a lambda abstraction, that is to be a predefined function, or it is an abstraction like lambda x dot E3, then the application is meant to be replacement of this x by E3, by replacement of this x, replacement of this x by E2 in the entire body of E3. So in E3, wherever x occurs, you replace that by E2, and that will mean the application. So let's take the example of cube we took earlier. So lambda n dot n cube, then 2. So E1 here is lambda n dot n cube, which is a function abstraction, lambda abstraction, and E2 is a lambda expression because which is 2, which is a constant. So when we apply, then E2, which is 2, is replaced in X, which is N, in the body N cube. So we do it 2 cube, or we can do it in terms of other notations of lambda as well. So in this combination, obviously, if in this combination E1 is not an abstraction, then this expression is syntactically correct, but semantically, as we'll see, it is meaningless. Because if I say 2 applied to 3, just within parentheses, I write 2 blank 3. Then it is syntactically a lambda expression, but it is meaning-wise, it has no meaning. So for this function application to have a meaning, the first lambda expression will have to be an abstraction. So we can say that in terms of what we often see in programming languages, so E1 is like an operator and E2 is like the operand. Right? So we often call E1 as from operator, the term derived is rater, and from operand, the E2 is called the rand. So we will often call rater and rand. So the rater will mean the operator or the function abstraction, and rand will mean the lambda expression on which that function abstraction is actually applied. So uppercase letters and identifiers beginning with capital letters will be used to define meta variables ranging over lambda expressions. Let me explain. I will explain that. Now, the associativity. If I have a function application, E1, E3, it associates from left. So it means that E1 is first applied to E2, and then this E1 applied to E2 is applied to E3. Right? So you might wonder that what sense will it make, because you have in your mind that if you apply a function, if you apply operator E1 onto operator E2, your mental set, I'm sure, is that you get a value. So like lambda n cube applied to 2 give you a value 8. So you will see what, if I get a value, then E1 applied to E2 within parenthesis is no more a lambda abstract. It's not a function. So how does it apply to E3? So please do not have that kind of a bias, because as we have talked of earlier, that certainly when apply a lambda abstraction to a rater, rand, then we can get another lambda abstraction. That is, often the functions that we have in lambda abstraction, often they are higher order function. So it's not necessary that the application of one abstraction to a lambda expression will give me a value, but it might give me a value which is a function itself. So there could be such chain function applications which are possible. We will see more examples to that. Composition is certainly the best example that we have. Now, in terms of the lambda abstraction, I write lambda x dot E1, E2, E3. Then the question is, how far does this binding of x apply? In the absence of a parenthesis, the binding of x onto this expression will continue as long as it can to the right. So here, if I write lambda x dot E1, E2, E3, it basically means that the body is E1, E2, E3. Lambda x dot E1, E2, and that applies to E3. So if you put a parenthesis here, what you're meaning that the extent of the binding of x ends at E2 and defines the abstraction which you are applying to E3. No, that is not the common notational process that the community follows. So it is lambda, as long as x can continue, without hitting a parenthesis, of course, then it will continue. Right? Then the fact is that the application has a higher precedence than action. This whole thing is an abstraction and that applies to E3, then I must put a parenthesis. Otherwise, it will not mean that. So you have seen without the parenthesis, what meaning does it get? Right? Now, if I have more than one variables in a lambda expression, then it is the alternate notation is you can skip the lambdas in between. So you can write lambda x, y, z dot e, which will mean that you have lambda x dot y, lambda y dot, lambda x dot, lambda y dot, lambda z dot, and then e. Right? Now, at times, now as I said, that lambdas are unnamed, unnamed. So a lambda expression is to be treated as the expression itself. Now this becomes quite difficult because every time I have to treat n cube, I have to write lambda n dot n cube. I mean, we human beings feel uncomfortable because we cannot handle that kind of extensive complexity. So we would like some different form of abstraction. So for that, in the impure form of lambda calculus that we are discussing here, we have something known as define, where you can define and give a name to an expression. Now, this name is not a part of the lambda expression, mind you. Be very careful. This is just a name given for human convenience of reference. So whenever we refer to that name, it basically means this expression. This is only syntactic, and that is what it has no computational parallel as such. It is just a way to refer to that expression in a convenient form. So if you would recall macros, it is like those manifest constants, particularly, not macro with parameters. But if you recall macro with used for defining manifest constants, it's just like that. So it is, the name is textually taken to be the expression that it stands for, and it will be replaced in that place. So just to give you an example, we have define twice is the name. Define is the way to say that twice is just a name, not a part of the expression. Is defined as, written as equal to symbol, lambda f, lambda x dot f applied onto f applied onto x. So what can you make out of from this? F applies onto x. This is an application, right? Pure. So f certainly has to be a lambda abstraction. It has to be a function. And then it applies x. Certainly it will generate some value onto which f is applied again. So you are actually applying f twice. So that is the reason I call it twice. So let's say if we instantiate this, if we now try to use this in the application. So I said twice, which stands for this expression. And then we put two rands, two operands. The first operand f has to be an abstraction. So I say this is lambda n dot add n1, where add is assumed to be a predefined function constant, operation constant from the domain of natural numbers. 1 is a constant numeral and n is the bound lambda variable. So what does this give me? This entire thing gives me that if I pass a value n, it will add one that and give me that. Okay? So, and then the second rand is x. Second operand x is 5. Right? So this is f and this is x when we put in the twice. So what will happen? If I do this, it will first do f will be taken as this abstraction, lambda n dot add n1, and x will be taken as 5. So then we will have this application, f applies to x. So basically lambda n dot add n1 applies to 5. So n becomes 5, 1, which means I get 6. So now I have f applied onto 6. F is add n1 again. It applies onto 6, so I'll get 7. Right? So that's a simple way to do the evaluations. So if we look at in terms of parallels in C again, then C also we have variables. We have constant operations which are known a priori, like multiplication, binary multiplication, or constants like numerals, which is 2. And then we can have function abstraction. Mathematically, we have seen this. Cube n is n cube. In terms of lambda notation, I can write lambda n. I'm defining now cube is not the function. Cube is just a name for reference of this lambda expression. So I have defined cube lambda n dot n cube, or I can write it in a little bit of a longhand form. And this is known as untyped lambda, because it does not say that n has to be integer. It could be integer, it could be double, it could be float, it could be matrix, anything, right? So I said this is untyped lambda. Alternately, I can write lambda n colon int dot n cube. This colon is additional, which looks pretty much like the normal programming languages, which is called a typed lambda. We will talk about typed lambda later on. Right now, we are assuming that everything is untyped. But it is possible to add type. We'll see that. So typed lambda. Which says that your parameter is of type int. The return type is not specified here. The return type is inferred. That is, it's inferred from the two facts that one is the function, the n is int, function is n cube. So it is twice multiplication of 2 ints. And we know that if we multiply 2 ints, we always get an int. So we will infer that the return type is int. We will talk a lot about this in a separate module. I'm just trying to show you the syntactic similarity or the variants that exist. In terms of a C function, we will write like this, where cube is the name placeholder, parameter type C is typed, so you have int n. You have the first same function body, and you specify the return type explicitly. Right? You do not leave it to the compiler to infer, you specify it explicitly. This is what the C programs require. So does the C++. In C++, now you can write lambda functions. So you write it pretty much in a similar notation, syntax as lambda n dot, or say lambda n colon int dot n cube. Look at the body, this is n cube. This is always the same. This pair of square bracket is a placeholder equivalent of lambda in C++. So this says this is a lambda expression in C++, takes a parameter n of type int. In C++, everything is strongly typed, so you cannot hope to have untyped lambda. So there's a type lambda. And it just defines the name of this lambda expression as cube. You can see the parallel between the lambda notation and this notation in C++. So cube becomes the name of this expression, right? So it's like cube is a variable now. It's a variable which means a lambda expression. This is what you get in C++. Now, what is the return type? Return type is not specified, so it is inferred. And C++ introduces a keyword auto. I mean, it is not strictly correct to say that it increases. C auto was there in the language earlier, but it had a little different meaning, which has been deprecated, and a new meaning has been given. What it means is to define a variable in C++, you need to define its type. So auto says that the type is not given by the programmer, but will have to be inferred from the initialization that you have. So here the initialization is this lambda expression, which is n cube, taking an int n. So obviously the compiler can infer that this is int. Alternately, you can write it as int cube, like that also. The other way to explicitly write the return type, you have a notation here where you write the same lambda expression, but between the list of parentheses and the function, much like the pointer dereferencing, and put the return type. So you can see that the position of the return type is very different from what it is in a normal function. You first put the return type and then the function name, then the parameter list. Here, first you say it is a lambda, the parameter list, then the return type. And certainly you don't need to give it a name. If you are willing, you can define it as a variable. And certainly when you say auto here, the value of auto would actually be int, because you have said, mentioned here that the return type explicitly is int. So these are the equivalent notations you have. In terms of the function application, in mathematics, we'll just write cube 2 will give us 8. In lambda notation, we'll do application. In C or C++ lambda function, we can. Cube has become a variable, which is actually a function, which is actually a lambda expression. So cube 2, this notation will mean this application. So we can make that application, and n cube will be set to the value 8. Okay? So this is, I could have, instead of cube, I could have simply written that entire expression right here. It's also possible. We will come to all of that details later on. We will talk extensively about lambdas in C++. I'm just trying to show you the range of notations or syntax that are possible. So in terms of the lambda expression, if you have to evaluate a lambda expression, then you will need to know what is the order in which the operations have to be done. So you can convert a given expression into a fully parenthesized expression following the rules. So let us try to follow the rules and see what different parenthesizing that we actually need. One is here you have lambda y dot goes to gy. So you apply the rule that the binding of y in this lambda goes to the rightmost that it is possible up to this parenthesis. So this becomes a lambda expression with this parenthesis. Once you have that, then you can note that extent of binding of g goes up to this end of the second expression lambda y. So you put a parenthesis to get. So this lambda expression within parenthesis becomes fully parenthesized here. Here you already have this parenthesis. You have lambda x and dot f and this. So x goes up to the maximum extent. Here, this pair of parentheses around nfx is balanced, so it goes up to the next parenthesis. So that is your first innermost expression. You put a parenthesis to mark that. Then you have f, which goes up to the last extent, parenthesize that. You have n, which goes up to the last extent, you parenthesize that. So you have parenthesized everything, now put it back. So the completely parenthesized expression corresponding to the given expression is this. This now clearly tells you what applications and abstractions are happening in this lambda expression. Now, as you keep on practicing writing and evaluating lambda expressions, you will get used to doing this mentally. But at least initially, or whenever you are a little bit confused, it is always good to first have a completely parenthesized expression so that you do not make any mistakes. And then do the evaluation according to the parenthesis, then it becomes a relatively mechanical process which will be error-free. Okay, so that was about the notations. Let me stop here for a while and see that how you're doing in terms of the notation. Now, next would be to take up different examples in terms of the notation that we have introduced. So I've stopped the presentation. Please unmute and ask if you have any question. No questions? Everything is clear? Yes, please.
So in C++, basically when you define the lambda function, so it can also be done instead of using the auto keyword, like function, then square bracket, then input, like what's the input parameters followed by the output parameter, right? So like
you are Obijoy, right? So please understand, the auto is not part of the lambda expression. Lambda expression is what you are initializing that variable with. You may not initialize a variable with a lambda expression. You can just use a lambda expression wherever you need it directly, right? So auto cube, as we wrote, then initialized with the right hand. That's what I have been telling for some time, that it is like auto cube is like defined cube. That is, you are giving this a name cube. Now, how do you deal with a name in a programming language? A name has to be a variable. So it is a variable which has a value which is a lambda expression. But the lambda expression is what you write as an initialization value after the initialization symbol equal to. So I could define a variable, set its set its type as auto. Let the compiler derive that. But technically, then auto is not is actually not just int in that example. Auto is actually a mapping from int. It's a lambda expression. It takes an n, gives you an n cube. So your input parameter is of type int, the output parameter is of type int. Right? Now, only when you apply cube onto an integer, the result is an integer. So what is auto? The auto in this case is a function mapping from int to int, for which you do not actually have a notation. Right? You do not have a notation to write this kind of type in the compiler or in the programming language. So you make use of this, which is basically to express the type of a variable or deduce the type of a variable from its initializer, which is a constant. So here the initializer value lambda expression, because you have given that expression. So it is that expression what is initializing. And auto derives the type for the variable that you have used to name that lambda expression as a mapping from int to int. Are you getting the difference over here? This is a very good question, and it's very critical understanding is that do not take that cube has any separate meaning. It just stands for that lambda expression. So instead of defining it cube, I could have just written that entire lambda expression, and then within bracket I can write 2, and that will apply on to 2. Yes, Abhijit.
Yes, sir. And, like this is possible. Like we finally like the return type can be directly written like the function mapping. We are completely replacing by auto at the beginning of the programming language, at the beginning of the like syntax for the lambda function. So this is possible because like C reads from right to left, right? If it would have been the reverse, then probably
C reads from right to left means C reads from left to
so
right.
like
It's English. It's English.
while compiling.
The compiler reads
So like
from
if
left
we have
to right. It does not read from right to left. Who told you it reads from right to left?
like,
The fact that it reads from left to right is the fact that you first write the type and then you write the variable. So that you have enough knowledge about the type when you meet the variable. I mean, maybe I didn't get your question.
like what I was saying is, suppose we are initializing a few integers. So like suppose our statement goes like this: int x comma y equal to x. So this is not possible, right? Because we have not yet defined x until we are assigning y to x, right? So is the case
Yes.
similar?
It is not, because those are, please don't confuse between syntactic shortcuts and semantics of the language. The fact that you can write int x, say int x, let's not complicate, let's say int x initialized 1, comma, y initialized x. This is valid, right? Or even int x, comma, star p initialized ampersand x. This is also valid, right? These are just syntactic shortcuts of writing separate definition for declarations for each of these variables. Don't confuse that with any evaluation. It does not do any evaluation in that. It is just a syntactic shortcut. Okay. In that, if you are referring to, in that, the comma that separates x and star p initialized with ampersand x, the comma that separates is not the comma operator. It is the comma as a list of different variables, all of which has the same type. Are you getting that? Comma operator which works from right to left. That's a different thing. This is not a comma operator. This is not an expression. Operator's precedence or associativity comes in when you have an expression. Every symbol is overloaded. I mean, most of the symbols are overloaded in the language. So when you are using comma here, the notation simply is a list separator, nothing else. So you could have just written it in different lines and it exactly means the same thing. Are you getting me over here?
Yes, sir.
Got it? Yes. So we will, I mean, I do not want to spend a lot of time on this here, because I have a separate module, two separate modules. One where we will talk about handling of types for lambda. And then we have a completely separate module talking about how does C++ handle the lambda expressions, which to me is something very interesting. Till C++ 11 came, I did not used to get so excited with the lambdas, because it was only limited set of functional programming language with a very limited community using it. But once it got introduced into C++ 11 and several STL components were developed based on that, and several powers of functional programming were available in C++, then that excites you, because now you have on one side the power of doing general programming that you are doing, and you have the power to do functional programming whenever it becomes convenient, particularly in terms of defining very mathematically correct expressions, which are very required for if you want to prove your functions correct. You could remain in the domain of lambdas, and that makes the things much easier for the theorem prover to prove, which is not so if you had written that same function in terms of a C function notation. So these are all different things that we are going to talk about. Here, what I'm trying to highlight, and the reason I am regularly referring to the programming language is we all know programming language. The reason we are referring to algebra is because we all have done algebra. So all that I'm trying to show is this lambda notation is just a little bit of reorganization on that, with a view to keep things very clear in simple three types of things only: variable constants, abstraction, and application. And we get the entire power of what we do computationally, which makes it equivalent to the Turing machine. Okay. Any other question? Please feel free to ask questions right at this stage, because these notations will be extensively used henceforth through the entire course. So if you have doubts, it's good to get clarified. Like, no questions. Okay. So let me start with some examples of lambda expressions, which are, these expressions are, they not only are useful, but they are very, very commonly used in different lambda exercise. So let's start with the very simple elementary expressions. The first is an identity. So I define ID, again, this is a name, for the lambda x dot x. This is an identity function. What is an identity function? An identity function is which gives you the same value for every argument that you may pass on to it. It gives the same value as of the argument, right? So if you try to evaluate this, try to apply this lambda expression onto some lambda expression E, you don't know what that is, whatever it is. It could be a variable, it could be an abstraction itself, it could be another application or whatever. Then what will happen? You will replace x by E in x. So what you'll get is E. So what is the type of E which you do not know? Given E, you are getting E. So it is an identity function which maps from domain A to domain A, where A is any type whatsoever. And actually, these kind of functions are often known as polymorphic functions or polymorphic operations, because they work for multiple types. So this is an identity function. And again, note that ID is not a part of the lambda calculus. It's just an abbreviation for lambda x dot x for our convenience. The second, what we have already seen, is known as a successor function. Often we write it as UCC, which is somewhat domain specific, because in every domain you may not have the successor function. But in natural number domain, you have add n1, which is a successor function. So if you apply it on some numeral constant, it will give you the next numeral, which you have already seen. Then you have the constant function, lambda x dot lambda y dot x. So a constant function is one which returns a constant value irrespective of the value of the parameter. Right. Now, this actually is, very strictly speaking, this is not the constant function itself. Rather, this is a kind of a hyperfunction which generates constant functions. So just look at this derivation below. K is lambda x, lambda y, x. So what is K0? Where 0 is a constant numeral. What is K0? K applied onto 0. If I apply K onto 0, x is replaced by 0. So it becomes y dot lambda y dot 0. Now, lambda y dot 0 is a constant function, right? Because no matter, since 0 is a constant and it has no occurrence of the bound variable y, no matter what I apply it on, it will always give me the value 0. For example, if I do lambda y dot 0 applied on to 17, the value will still be 0. Lambda y dot 0 applied on to 935, the value will be 0. So it always gives me a constant value 0. So this is k0 is a constant function which always returns 0. Similarly, k1 is a constant function which always returns 1, and so on. Kn is a constant function which always returns n, and so on. So k, which is lambda x dot lambda y dot x, is a generator for constant functions. I think I'll stop here because we have very little time left to talk about composition. I want to spend more time on that. So just let me finally check if there are any other questions. Is there any question what we have discussed so far? We have introduced the basic syntax of lambda expression and talked about the precedence and associativity of the two operations that lambda expressions have. One is of application and one is of abstraction. And based on that, we have seen parallels with the common programming languages, and also it started introducing some elementary lambda expressions. If there is any question, I can quickly respond. Okay, it seems it's clear. Showman, have we uploaded these slides? Module 2? No.
No, sir. Module 1 is uploaded.
Okay. So I'll send you module 2. You upload that so that people can go through this part. And then in the next class, Wednesday, we will continue on this and talk more about varied forms of well-known lambda expressions. Thank you very much. Have a nice day.